Hi, my name is Nithin Sivakumar, and I'm a junior. I'm coming to you guys from Dallas, Texas. I'm very interested in the field of data science, which is what my project is going to be about. Today, we'll be looking at a comparative analysis of fake news classifier models. Big thanks to my mentor, Mr. Jim Shepish, who really helped me throughout the entire journey. All right, so first, let's talk about what is fake news and get a little bit of understanding for the problem. Fake news stems from social media, and social media is everywhere. Social media has expanded its reach and influence through different news outlets and information sources. And in these sources, a few people use their secret agendas in order to promote false or misleading information, which can be spread very quickly. This phenomenon is known as fake news or misinformation, and it undermines people's abilities to make informed decisions, whether it be political or just to their daily lives. Surprisingly, 62% of adults get their news on social media, which is up from 49% just in 2012, according to a 2018 study by the Pew Research Center. This drastic increase just shows how many people are migrating to use social media from different forms of news, such as TV or newspapers. And furthermore, children are especially vulnerable to being deceived by fake news. And with the growing popularity of generational apps, this only enrages this issue. A 2020 study by Stanford University found that false information was found in a whopping 72% of tweets related to the COVID-19 pandemic. And the COVID pandemic being a worldwide thing, this shows just how much pieces of information can be misleading. And some additional statistics, only 26% of Americans share that they are confident in their ability to recognize fake news. This is not a lot in the real scheme of the grand. Furthermore, Americans who believe fake news causes a great deal of confusion is a high number of 67%. And Americans who accidentally shared fake news online is around 38.2%. And these are only people who have now realized that. If we were to look at people who still do not know that the information they have shared can be fake or misleading, then the number would be even higher. So let's talk about the spread of fake information, how this can happen. Let's say we have a person here who decides to tweet out a certain piece of message. This tweet is received by another person. Let's say this man finds this tweet to be pretty interesting. What does he do? Well, he sends it to a few friends and family members. Now, these people find this tweet to be interesting. So what do? Well, they send it to more of their friends and family, and they send it to their friends and family. And soon enough, you have this wide network and web of people who have been circulating a single tweet. And just in a matter of days, this tweet can reach millions of people because with the power of social media, everyone is just one click away from sending a piece of information to anyone online. So now that we know the problem, well, what can we do about it? Well, this is where artificial intelligence and machine learning comes into play. Let's say, for example, we had an artificial intelligence algorithm that could be implemented at the root of this problem. In this case, if a certain algorithm was able to predict that the very first piece of information that was tweeted by this very first person was fake, then all of these shares could be cut off and the fake news could be contaminated really simply. So now let's move on to the study. The research question we aimed to solve was, what is the most effective way of detecting fake news on a text-based level? And our purpose was to compare the performance of different machine learning algorithms in detecting real versus fake news within text-based political articles. And to do so, we looked at three main machine learning algorithms. First, we have Naïve, which is a probabilistic algorithm used in machine learning for classification, classifying tasks. We'll get into more detail about this later. Next, we have random forest, which is an ensemble learning method, which simply means that it will combine different other methods in machine learning that builds what is known as decision trees. Once again, we will cover that later. And it combines the outputs of these trees in order to improve the accuracy and robustness of the overall predictions. And finally, we have support vector machine, also known as SVM, which is an algorithm that can be used for classification or regression tasks, which uses a hyperplane in order to separate data into different classes. Now let's take a closer look at each of these algorithms. First, we have Naïve Bayes. Naïve Bayes is a classification algorithm that uses what is known as Bayes' theorem in order to calculate the probability of a given data point of a certain class. Naïve Bayes is also a probabilistic algorithm. Now, these big words may sound confusing and daunting at first, but for the purposes of this study, we will focus on why it is called naive. And this is because it assumes that all features are independent of each other. In other words, if we were to pass in a string of words into a naive-based algorithm, it would analyze each individual word independently of how it looks at the other words, and therefore can have certain pros and cons depending on how we use this model. Naive Bayes overall is a fast and simple algorithm which can be used for text classification tasks, which is very important for sentiment analysis, which is basically the analysis of words and how information can be conveyed through them, which is very important for a study we will be looking at today. And finally, Naive Bayes can handle high-dimensional data sets, and because of this, it is a popular choice for natural language processing, which is another keyword that we will be looking at today. Second, we have random forest. Random forest is an ensemble learning method which combines the decision trees that we mentioned earlier. Essentially, a decision tree is a set of rules, and the random forest divides the data set that is passed into as input into various decision trees, which then use specific rules in order to analyze each part of the initial data set. The random forest model is called random because it randomly selects a subset of these features to build each of the original trees. And this helps improve the model's generalization performance, which essentially means that if you were to scale a random forest model to a larger occurrence, it would function quite well. The random forest can also be used for classification and regression tasks, which can handle both categorical and numerical data. And overall, it outputs a probability score, which can be used as a versatile algorithm, which handles various types of data. Finally, we have SVM. SVM essentially uses what is known as a decision boundary or hyperplane and maps the data that is passed into it onto this hyperplane and predicts it as a continuous output variable. SVM then identifies what is known as support vectors in order to find the points that are closest to this hyperplane and then use that to calculate the margin or distance between the different classes. This allows it to handle both linear and nonlinear data. While this may sound daunting as well, essentially what this algorithm does is calculates what is known as a line of best fit or a regression line and uses the residuals in order to figure out which ones can be classified as what in the parameters that is originally given. And overall, this allows it to work with a wide range of data sets, especially when there are few training examples or when the data is high dimensional. Now we'll look at the hypothesis of our study. At first, we hypothesized that the random forest model would theoretically provide more robust results because it has reduced variance, reduced overfitting, and less bias. Reduced variance refers to the idea that through multiple trials, the random forest model will not have significantly different results. Reduced overfitting is a term that we will look at later more in depth, and less bias simply refers to a model having a higher probability preferring a certain class or feature over a different one. Now let's look at the methodology. For our data, we found 3 corpora that were listed on the online source Kaggle and found 3 political articles that were scraped off a variety of web sources. In order to process, each data set essentially had a large list of article entries. And for each article entry, we concatenate the title and body of each of the article and put it into a process called cleaning and normalization. In that process, we remove the stop words, which are essentially words that are irrelevant to sentiment analysis. For example, words like the and a, which can be used a lot, do not provide to understanding fake versus real news, and therefore are removed. We also convert the text to lowercase, remove HTML tags, usernames, URLs, and numbers. And finally, the data is then passed into what is known as a count vectorizer, which essentially processes the data so that it can be understood by the machine learning models. In terms of experimentation, we would take what is known as the scikit-learn library in order to create these 3 different machine learning algorithms in our code. And each model was passed into 2 types of validation. First is 5-fold cross-validation, which essentially takes one data set, divides it into 5 parts, and would train and test it on each of those parts. The other term is known as external validation, which uses more than one data set. Here, each model is taken and trained and tested on all 3 of the data sets. In terms of settings, we would set Naïve base to default, random forest to creating 200 trees, and the SVM would be passed into the standard scaler and gamma automatic. Essentially, what these settings do is set the conditions so that they are similar across all three models. Now let's talk about the results and discuss what they mean. Firstly, the Naïve-based classification experiment showed high accuracy, sensitivity, and precision, which can be seen in this left graph, which is the cross-validation accuracy. These numbers were in the 0.8 to 0.9 range, which are relatively high. And what these indicate is that the model was able to effectively identify what is known as a positive instance, which essentially means it was able to identify the fake news present in the articles quite well. Furthermore, it had a relatively lower specificity score, which is about the 0.75 to 0.8 range, which suggests that it had difficulty in accurately identifying the negative instances or the actual real news. Naïve-based classifier assumes independence of all features, as we talked about earlier, and this may lead to its lower specificity. Smaller standard deviations for the accuracy and sensitivity scores, which were about 0.1 to 0.2, and precision suggests that it had consistent performance, which also expands on why it is a overall good model to use in terms of fake news classification. But however, these results are only specific to cross-validation, as when we looked over to external validation, the model experienced what is known as overfitting. Once again, we'll come back to that topic later. For the random forest classification results, we see that it also had a high level of accuracy, precision, sensitivity, and specificity, which is in the 0.8 to 0.9 range, which is similar to the Naïve-based model and can be seen in the cross-validation accuracy. This means that the model is pretty good at identifying the positive and negative instances in the data. Once again, that is identifying fake news and identifying the actual real news for a large proportion of the data. Then the F1 score, which is in the 0.8 to 0.9 range, indicated that the model had a good balance between two other statistics known as precision and recall, which are important for avoiding bias towards one specific class or feature in the input data set. However, once again, similar to the Naïve-based model, it experienced high levels of overfitting in the external validation. Finally, we have the support vector machine classification results in discussion. Here, we can see that the model also showed high accuracy and specificity, which is about the 0.85 range. However, it struggled in achieving strong sensitivity, negative predictive value, and F1 score, which are in the 0.75 to 0.8 range. This suggests that the model had some discrepancies in accurately identifying and classifying fake news, which means while it was able to understand the actual real news and identify that relatively correctly, when it came to fake news, it struggled a little bit more than the other models. The low F1 score, which is in the 0.6 to 0.75 range, indicates that the model has a bias towards precision rather than recall. This bias indicates that the model does not correctly identify the true positives or the actual fake news, or it incorrectly labels the actual real news as false positives or fake news. So essentially, if we were to pass in a certain input data, it would understand the real news as fake news in certain scenarios, which is a big issue in allowing free speech to occur in the real world scenario. However, once again, we see a common pattern that it also experienced overfitting in its external validation results. So now let's talk about our conclusions and the insight we can gain from this study. I've said the word overfitting multiple times, but what really is it? Well, firstly, overfitting is when a certain model performs well when tested on the same model as it was trained on, but not others. For example, in our study, let's say we were to have a random forest model that was trained on dataset labeled B, and then it was tested on dataset A, B, and C. Overfitting means that when it was trained on dataset B and tested on dataset B, it would provide good results. However, when it was trained on dataset B and, for example, tested on dataset A or C, it would have significantly lower markings. These are known as null values. Null values are when you have accuracy markings of around 0.5. These indicate that the model performs similar to having no model at all. Essentially, this means that the model had what is known as a coin flip. Instead of actually understanding the data and being able to provide insight and help classify, It's simply performed as if someone were to just coin flip every time they had a certain article and classify it based upon that. Overfitting occurs when a model has learned what is known as the noise and variability of the training data, which includes the outliers and irrelevant patterns present, instead of understanding the underlying pattern. This means that the model will copy the exact input data into its system rather than understanding the true semantics given. This makes the model not robust, as it cannot be generalized to a larger scale. For example, in the real world, there are an infinite number of ways data can be shown. Every single person writes in a different way every single time they touch the keyboard. So if a model can only understand one instance of one person writing, then it will not be able to identify real fake versus real news in the real world setting. So let's talk about some future studies. Firstly, our initial hypothesis that the random forest model would outperform the others was incorrect, as all three models experienced overfitting and therefore had the same level of results when looking at the larger scheme of things. So in future studies, it's very important that the advancement of machine learning algorithms can tackle the pervasive problem of overfitting. We truly need to solve this issue, because if not, you'll never be able to create a model that is able to detect fake news at a variety of different sources. Thus, we can use new studies that can help try incorporating dropouts into neural networks, conducting rigorous feature selection, or exploring innovative feature extraction methods. These are three different ideas that all help isolate and analyze specific features more into depth of each input data. This way, if we analyze the data even more, we can help the model not overfit and help just understand the underlying data. These endeavors should aim to create models that can handle complex data sets. Like we talked about before, the real world has a variety of different ways news can be presented, especially with text and social media. So if a model can understand and detect fake news in any setting, it's absolutely crucial that it can understand complex data. And finally, future experiments may also try to combine different algorithms in order to increase the effectiveness and provide some more robust results. In the study we looked at today, we simply took out 3 specific machine learning algorithms and separated them into 3 models instead of combining them. However, because each model has its own pros and cons, combining them may have a possibility of allowing a scientist to get rid of some cons and maybe even solve the problem of overfitting, as we saw. Thank you so much for listening to this presentation. I hope you guys learned something about fake news and how it functions in the real world, and hopefully we can find a solve to this issue in the near future. Thank you so much.
I was just wondering, like, why were those the 3 machine learning algorithms that you selected? Were there, did you explore using other ones?
Yeah, so when we first started this, we thought about looking at different ones that were more semantic related, but because these are the most common when it comes to fake news, because there have been other works that, and I wrote a paper on this, so that we dive a little bit deeper into it, but these are the they're most accessibly easy to use because the library we used already had, I guess, a template for these ones that we could kind of follow. So that's mainly why we looked at it. And they were the most broadly talked about in this field of fake news and other papers. So yeah.
Gotcha. And like I asked other people, how did you get interested in all of this?
So I guess how I got interested in this is, well, so I was trying to figure out something that, because I've always been interested in computer science. And when I was looking at, like, I wanted to do like, all right, so I've taken a few courses about it. I've done watched a few boot camps, but what can I really do to actually help this field? That's when I started to do some research, and I got into, I guess, a subset of computer science that's also related to the field of like society, as you can see by this presentation, and that was called data science. And this is more, I guess, it implements statistics and it looks at, I guess, larger world connections that you can use with computer science. And from that is where I was able to get into this idea of fake news, because if you look at the world, especially in today's society, everything revolves around news, and especially with like TikTok, Snapchat, and a bunch of different new apps that are popular with younger generations. Social media is at the head of that. And that's kind of, yeah, and fake news kind of interests me because it's such a widespread issue. And I find that there's no like one like everyone, like one solution that all scientists can agree on. All papers just kind of build on each other. There's nothing that's really like concrete. So that's kind of what got me interested into this.